So there were, as we already know, n number of patterns initially, and each pattern like x1 was distributed over p number of features, x2 again was distributed over p number of features, and in the same way nth was also distributed over p number of features. We excited these patterns at this layer, and the RBF layer expanded them to a higher dimension, and the next layer is to be used for actual learning or actual classification. Now let us look at other representation of these radial basis functions along with these weights. Now let us go to the first pattern, excitation. Means pick up the first pattern x1, apply it at the input layer, means x1 goes here, x2 goes here, and xp goes here, corresponding to the first pattern. Now think about this calculation, that is phi at first neuron of your radial basis layer. This calculation of your radial basis is denoted by phi 11. Phi 11 means pattern number 1 and output for pattern number 1 at first neuron of your hidden layer. In the same way, this denotes pattern number 1 means output of radial basis neuron number 2 at hidden layer corresponding to pattern number 1. And in the same way, this denotes output at mth radial basis function neuron corresponding to first neuron. Now pick up the second pattern, that is x2, excite it at the input layer. So this feature corresponding to the second pattern will be represented using phi 21. Means second pattern neuron number 1 given by phi 21, second pattern neuron number 2 given by this phi of 22, second pattern neuron number of m is given by your term phi of 2m. In this way, represent all patterns which were total n in numbers using a matrix of dimension n is to m. So this is your radial basis function matrix representation. Okay, this was the representation of your radial basis function along with your input patterns. Now think about the representation of this layer, weights involved in this layer. Now let us suppose there are s number of classes in which the patterns were to be classified. 1 to s number of classes were there. So there will be s number of neurons in the output layer. Now let us think about the weight vector for first neuron. Weight vector means all the inciting weight at neuron number 1. So neuron number 1 has W of 1, 1, and it has W of 2, 1, it has W of M1. So these are the weights being incited at neuron number 1. So these weights are given by using this first row. Using this first, now these all these weights are to be given by using your column number 1. This column gives your W of 1, 1, this one W of 2, 1, this one W of 3, 1, this one, and W of M1 using this one. So overall output corresponding to this neuron will be calculated by picking first row of this matrix and first column of this matrix, and then phi 11 multiplied by this weight plus phi 12 multiplied by this weight, and then plus phi 1m multiplied by this this W of M1. In the same way, the input vector at the second neuron, let j be equal to 2, can be seen as the multiplication of this row and corresponding to this one. And one thing more to clear is that in case of this radial basis function neuron, each pattern P, not P exactly, each pattern X is supposed to get equal chances for classification into 1, 2 up to S number of classes. It means for every inciting pattern X, we have to calculate its outputs corresponding to the first neuron, corresponding to the second neuron, and corresponding to its sth neuron. And one out of these all is going to be equal to 1. that may be based upon some logistic function. That may be based upon some logistic function or some other parameters. So let us just again revisit the calculation of weights for the first pattern. Now the first pattern will come, that is x1. It will be going inciting here, then it will be extended in m dimensions here. Then after extension to m dimensions, the output at this neuron will be calculated. How it will be calculated? Just by multiplication of this row to this column. It will generate a value, suppose a. Then again the belongingness of this first pattern again with the second cluster will be calculated by multiplication of this row to the second column. Let it be b, and the third relationship of first pattern with the sth cluster will be declared by multiplication of this first layer with your sth column. So in a way, each pattern will be having your s number of outputs. They may be altogether different. Maybe one out of them all will be 1 and others will be 0, and hence concluding that pattern number x1 was belonging to the class which resulted in 1 at the output pattern. Now let us see the process for the second pattern. Suppose second pattern x2 was incited upon and the corresponding radial basis function row was your this one 5 of 2 1 2 2 and up to 2 of m. Now for finding the output corresponding to the second pattern, this row will be picked, and when it multiplied by this first column, it results in your belongingness of this sample number 2 to cluster number 1 or class number 1. When this row is multiplied by the second column, it gives the belongingness of second pattern to class number 2. When this second row is multiplied by your third or sth column, then it gives the belongingness of this second pattern with your class S. Means to say, each pattern X, there will be certain belongingness to class 1, 2 up to S. They may be 0, 0, 0, 1, 0. They may be of this nature, and which says that this pattern x2 or xj belongs to the class where this value is equal to 1. In the same, okay, now let us try to redraw or recalculate these matrices in a better and more clearer way. So there were n number of samples, each distributed over p number of features. N samples were there, each was distributed over p number of features, and s number of classes were to be formed. And we just discussed about the formation of this phi of 1 1, this phi of 1 2 up to this phi of 1 m, then this phi of 2 1, this phi of 2 2 up to phi of 2 m, up to phi of this n1, up to phi of this n2, up to phi of this nn, and correspondingly the weights or weight matrix is also given, which was represented the corresponding weight vector connecting your RBF layer to your output layer, means this layer. We are talking about this layer. Now these weights, weight at neuron number 1, weight at neuron number 3, and weight at neuron number s. Suppose there are 1, 2 and s number of classes are to be formed. So weight vector this w1 can be seen as w of 1 1, means weight connected between hidden neuron number 1 to output neuron number 1, weight connected between hidden neuron number 2 to output neuron 1, and in the same way weight connected between this mth neuron of your hidden layer and first neuron of your output layer. So these columns gives this weight vector for first neuron, this column gives weight vector for second neuron, this column gives weight vector for your sth neuron. So s number of classes are to be formed corresponding to this. And we have already provided with the class labels. As there are n number of samples, so we'll be having a vector of containing n values, each corresponding to a particular sample. So sample number 1 was belonging to class C1, it was belonging to class label C2 and up to Cn, where all Ci's can have values from 1 to s. It means that it can be 0, it can also be 0, it can also be 1, it can be 2, it can be s. So s number of class labels were there, and this vector contains the values from this set s. So we are having this as our final equation, and in terms of vector it can be written as that phi dot w will be equal to your d, your desired outputs or your desired vector. So we know this matrix as it is coming from the procedure of finding your receptors as well as your standard deviations for the hidden layer or your RBF layer, and this D, this desired labels, we already know. The only unknown thing is this one. So we can find out this by using W is equal to inverse of 5 multiplied by D. So this is our final equation to determine these weights. These weights were to be determined using this equation. And this all complete our functioning of a radial basis function based neural networks. Now we have gone through all the steps required for constructing a radial basis function based neural network. Means it started with your input layer distributed over p dimensions, then it extended these p features to n features, and finally we found these weights that are used to classify the input vectors. Now for input to your hidden layer, or you can say radial basis function matching, we found two terms. One was your receptor, one was your sigma. And for this layer, for finding these layers, we have to make use of phi of inverse of phi multiplied by your matrix D, means the term. Now just by using these two layers, we can efficiently look at a p-dimensional featured vectors and two m-dimensional featured vectors, and if and there are higher chances of separating them linearly and to have a better classifier, better in accuracy. Thank you very much.